The number of unused states in 3-bit Johnson counter is, here as there are 3 bits, possible number of states is 2 power 3, which is 8, and we know that n-bit Johnson counter consists of 2n states. N-bit Johnson counter consists of 2n states, which is 6 here. So total number of unused states is equal total possible states minus number of states, which is 2. Here correct option is option B. The number of essential prime implicants in the given K-map is, here let us find out the prime implicants first. We look for quads, then we'll go for pairs. So this is one possible quad. Here these two are don't cares. So we can take one, as we are as we can form a quad with those. So we are taking these two don't cares as ones. So this is one more quad, and this is one more quad. So this is one pair, and this is one pair, and these 4 also can form a quad. So here number of prime implicants are 1, this one quad 2, this one more quad 3, this quad 4, this quad 5, and this is 6. So total we have 6 prime implicants. In that we have to find essential prime implicants. Essential prime implicant is nothing but a prime implicant which consists of at least one min term which is not covered by any other prime implicant. So if we see this quad here, this one is exclusively covered by this prime implicant. This one is not covered by any other prime implicant. So we can take this quad as essential prime implicant. If we see other quads, let us see this quad here, these two ones are covered by this prime implicant and this prime implicant, and these two ones are covered by this prime implicant and this prime implicant. So this quad is not essential prime implicant. Like that, if we see all the prime implicants, only this prime implicant, this quad consists of distinct one. So here number of essential prime implicants is 1, which is option A.
A 6-segment pipeline contains fetch instruction, decode instruction, calculate operand address, fetch operand, execute instruction, write operand. Each segment takes 1 clock cycle. We have 2 instructions I1, I2 in a pipeline. So this I1 is 1 instruction, I2 is 1 instruction, where R1 is appended with R1 star R2, R3 is appended with R3 plus R1. That means the result of the previous instruction we use in the next instruction. Instruction I2 execution started before I1 terminated. What is the number of clock cycles required if the operand forwarding mechanism is used? 9, 10, 7, 8 are the options. So here let us try this using the clock cycles. The clock cycles are something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and so on. First I1 we are execute fetch instruction, because each phase takes only 1 cycle. Decode instruction, calculate operand address, fetch operand, execute instruction, and then write operand. Okay. Instruction I2, the result is depending, but operand forwarding is possible. We can't fetch here itself, we can fetch here this case, fetch instruction. Again decode instruction, calculate operand address, fetch operand we can't make, because after execution only fetch operand will be done, because operand can be forwarded. Fetch operand and then execute instruction write operand. So at 8th it will be finished. Option D is the right option. Regular language with 4 states, 4 state DFA. The complement of L be L dash. The number of states in DFA accepting L dash is 3, 5, 4, 6. Actually, if L is a regular language and if there are 4 states in a DFA, for example, then the complemented language also contain 4 states, because only thing we have to do is we have to change the final state into non-final states and the non-final states into final states. That modification you have to make. Number of states remains same. Option C is right option. Following NFA. So these are the states 0, 1, 2, 3, 4 are the states. 3 is the final state. So the language, this is 0. The language accepted by the above NFA is. Normally the set of all strings accepted will be the language. Okay. So what are the paths here from initial state to final state? 1, 0 is one path. 1, 0 is accepted. In this path, 1, 0, 0 star 1. 0, 0 star 1. Or one more path can exist. 1, 1, 0 star 1. 1, 1, 0 star 1. These are the possible paths. 1, 0 is one path. 0, 0 star. 0, 0 star 1 is one path. 1, 1, 0 star 1 is another path. So you have to cover all these paths. So that is 1, 0 or 1, 1, 0 star 1. This will cover only one thing. Will not cover, option A will not cover the second thing. Option B, 1, 0 is there. 0, this will not cover this. 1, 1, 0, 1 will not be covered in the option B. Option C, if you take 1, 0 is there, or 0 followed by 0 star 1, which will cover 0, 0 star 1, 1, 1 followed by 0 star 1. So 1, 1 followed by 0 star 1. 1, 0 is already covered. So option C is the right option. Option D, 1, 1 is there, but 1, 1 is not there in the expression. Minimum string is not 1, 1. So C is right answer. It is a language recognized by the following CFG where productions are S2 AS, AS, BS or epsilon. So here if you take S2 AS or AS, BS or epsilon, minimum string is epsilon. Next minimum string is we can have small a. We can't have a string start with B. We can have a string start with A. At the same time, if you take S2 AS, BS, this S must be replaced with either with AS, again with AS, BS. That means S will be more than base. That means option B is wrong, because each prefix W has exactly as many A's as B's is wrong. Each prefix of W has at most one more A than B. At most one more A, two more A's also may be possible, because AAB also possible. Okay, but AAB in a prefix of AAB is AA, one of the prefix. This is containing two more A's than B's. That's why C is also wrong. So each prefix of W has at least as many A's as B's. That means we can have more A's, but minimum at least as many A's as B's. For example, if you take AS, BS, if both S are epsilon, you will get AB. A's and B's are equal. Either A's can be more than B's or A's, B's will be equal. B's cannot be more. Option A is right. Following finite automata, Q0, Q1, Q2 are the states. These are the transitions. Let S denote the set of all strings accepted by the above machine which are of length 5. How many such strings exist? Say for example, length 5 strings you have to find out. Minimum string is 1, 0. Actually, this is a DFA for all combinations of zeros and ones which are ending with 1, 0. So every string should end with 1, 0. Before that, you can have any combination. You can have 0, 0, 0, 0, 0, 1, and so on, 1, 1, 1. All using 2 bits of length 3, we can have 2 power 3, 8 combinations. So every combination will end with 1, 0. So you will get 8 strings. Option B is the right option.